Now we need to compare these two growth functions, one n squared, another n log n. Which one grows faster? Which algorithm is faster? All right. To do the comparison, so we use the way we did in the previous slide. Remember when we compare if the first term dominates the second term, that way, okay? The ratio of the two growth functions, and we take the limit when n goes to infinity. Yeah. So let's do the cancellation. After the cancellation, we want to calculate the simplified limit n over log of n. Yeah. This log, some of you may ask me, what is the base, right? Yeah. The base, so here, the base, because I didn't write the base here. Yeah. So here, let's assume we consider a general base, A. We only require that this base is greater than 1. That's all we need, okay? The base A of the logarithm greater than 1. Yeah. So, all right, so let's consider this, if you do not see the base, so for this class, if you do not see the base, so for this class, our log notations for this class. Okay, so we know there are several cases. All right. One is the natural log, the first one, natural log, base E, right? E, okay? Natural log base E. Second, this LG base 2. In this class, base 2. In math, base 10. Okay? Yeah. In math, if you, because math, people use LG, that's base 10. Okay? All right. So if you see LOG without specify any base, so base A, base general A, but the A greater than 1. Yeah. A greater than 1. Yeah. So that's our assumptions in this class. Okay. All right. Now, can you see the ratio infinity here? Can you see the ratio infinity here? N over log of n. Yeah. It may not be easy to see. Yeah. For you, if you do not have much experience in calculus, it may not be easy to see. Yeah. So to see it, there are two different ways to see it. Yeah. So here, I may talk about these two different ways to see why the limit of n over log of n, when n goes to infinity, is infinity. Yeah. The first way, we can do variable substitution. Yeah. Because the reason is, when we look at the log, we may not be very familiar with the log function, right? Most people may not be very familiar with the log function. So here we can use variable substitution to avoid log function in our expression. Yeah. So that's the first method. So we let u, a new variable u, be the log base a of m. So this time we write the log base a explicitly. Log base a. Yeah. Then based on the definition of the log function, we have n equals base a to the u. Base a to the u. Yeah. N equals that. Yeah. So with this new variable u, this time we can write the limit of the ratio of two functions n over log n to, this time we use the variable u, so a to the u over u. So the form, you can see, same limit in different forms. In the second form, the log function is gone. You do not see log function. Yeah. So you may feel better. Yeah. For those people who are not quite familiar with the log function, the second form is more friendly, right? Yeah, more friendly. So let's look at the ratio in the second form, how to interpret it, how to interpret this ratio. Yeah. The denominator function is u. U, we know it's a linear function, right? U is a linear function. Yeah. U function. Yeah. So the u function, u here, it's a linear function. And we know a linear function is a special polynomial, right? Special polynomial. Okay? Yeah. And the numerator function a to the u, exponential function, right? A to the u and exponential function. With the base, yeah, because the exponential function with the base greater than 1. Now we do comparison between an exponential function a to the u and a polynomial n. Then there is a fact, if you, in our everyday life, many times people say a fact like this: exponential function dominates polynomials. Exponential function, but when you say that, people ignore the base part. But you need to be aware of that. The base should be greater than 1. If the base less than 1 or equals 1, then it's not true. Okay? So only when the base strictly greater than 1, this fact is true. Yeah. So the fact is an exponential function dominates any polynomial. Okay? Yeah. But there is a hidden information that base should be greater than 1 for the exponential function. Yeah. So with this fact, you can also see the ratio is infinity. Yeah, ratio is infinity. Okay. Yeah. But this is method 1. Yeah. Method 2. Yeah. Later, I will use rigorous math. Yeah. But because here it's not a complete proof here. Yeah. Here just to show you some more information, give you the idea about the difference about this ratio. How large is the ratio? Yeah, yeah. But some of you may still like to get the rigorous proof, right? Yeah. So for the rigorous proof, we need to apply some calculus, some powerful calculus tool. Here it's called the L'Hopital's rule. the L'Hopital's rule in Calc 2. Yeah. So in the calculus course, Calc 2. So you learn this L'Hopital's rule. Yeah. Here, yeah, I can use L'Hopital's rule to prove that fact. Yeah. But yeah, sorry. Yeah. But in my exercise questions, I do not ask you to do this kind of proof. Yeah. Because some students worry about it. Yeah. Some students worry about, how much calculus do I require for this class? Yeah. Yeah. So here in my explanation, I use some calculus. Yeah. But when I assign homework questions, I do not ask you to do this kind of calculation. Yeah. All right. So method 2, use L'Hopital's rule to calculate the limits. Yeah. Limit of the ratio of these two functions. Yeah. All right. So here, the L'Hopital's rule, basically, the essence of the L'Hopital's rule, that is, when you calculate the limit of two functions, you can convert it to the limit of the ratio of two derivatives. That's the main part, main ingredient, for the L'Hopital's rule. Yeah. All right. But when you apply the L'Hopital's rule, there is a condition you need to check before you apply it. Yeah. You need to see if it is right to apply the L'Hopital's rule, the right situation to apply the L'Hopital's rule. Yeah. So that is, the ratio should be indeterminate form. Indeterminate form. Yeah. All right. So what's the indeterminate form? Yeah. Here, for example, there are several versions of indeterminate form. Yeah. The first one is we use infinity over infinity. Yeah. So what's that? There are two functions. So usually we consider two functions. F of m over g of m. The f of n goes to infinity where n goes to infinity. G of n also goes to infinity where n goes to infinity. Yeah. So then we call this ratio infinity over infinity form. Okay? So that's the meaning. Yeah. Do not understand that infinity over infinity literally as that infinity notation over infinity notation. You want to get what's the value of it. Do not understand in that way. Yeah. This is the form. Okay? Yeah. But what we call indeterminate, because when you have infinity over infinity, there are several cases it could be. This ratio could take several cases, all possible. Yeah. For example, the first case, infinity function over another infinity function, can the ratio be infinity? Yeah. It's possible the ratio could be infinity. Right? Yeah. So that's one possibility. Second, the ratio could be some constant not equal to 0. Ratio could be constant not equal to 0. Okay? All right. The third, the ratio is 0. It's also possible. The ratio could be 0. Okay? Then another case number 4, the limit does not exist. The limit does not exist. So you can see there are these 4 different cases. So that's the reason we call it indeterminate. Yeah, cannot be determined. Yeah. All of these 4 cases are possible. So you need to see what are those two functions, f function and a g function? Top function, bottom function. You need to know what are those functions. All right. So if we have this infinity over infinity indeterminate form, then we can apply this L'Hopital's rule. All right, so here, let me show you how to calculate this limit from the previous slide. When u goes to infinity, what is the limit a to the u over u? All right. First, let's check. Is it infinity over infinity indeterminate form? Yes, it is. When u goes to infinity, the numerator function goes to infinity, the denominator function goes to infinity, so it is an infinity over infinity indeterminate form. So we can apply L'Hopital's rule here. Okay? It's legal to apply the L'Hopital's rule here. Okay? And when we apply it, let's take the derivative of numerator and the derivative of denominator and do the calculation. Here, the derivative of the denominator is simple, right? The u, the power function. So here, we use the power rule. Okay? We call the power rule of the derivative function. The power rule tells us x to the n, it's a power function. If we take a derivative, it equals m times x to the n minus 1. That's the power rule. Okay? Yeah, power rule. Yeah. All right. Then the numerator function derivative, that's the exponential function derivative a to the x. Okay, the formula. Derivative equals natural log of a times the original exponential function a to the x. Yeah. Here our variable is u. Yeah. So you see the ratio of two corresponding limits. Yeah. After we do the simplification, because now constant part. Okay, constant part. Then when u goes to infinity, you can see the result goes to infinity. A to the u. Yeah. A constant times a to the u goes to infinity. Yeah. So you can see, a is strictly greater than 1. Yeah. So then it goes to infinity. That exponential function. Yeah. So in this way, you prove it rigorously. Okay. You prove it rigorously. Okay? All right. Yeah. Yeah. So here, yeah. All right. There is another detailed thing I may need to explain a little bit related to the rigorous math proof. Yeah. So here, in order to help you understand the detail in our calculation a little better, so here I explain a little more details. Yeah. But in the assignments, you do not need to do things like this. Yeah. Okay. All right. So here, let us calculate another form. Yeah. This time we do not use the variable substitution form, u. Here we go back to the original form with log function. Yeah, this form with log function, the original ratio form, n over log of n, when n goes to infinity. Yeah. And here for this function, you can see the variable, and we call it discrete variable. Why? Because n can only take discrete values, 1, 2, 3, 4, and so on. Yeah. N cannot take 1.1, right? 3.5, n must be positive integers. Yeah. So we call it discrete variables. Yeah. But for discrete variables, there is a problem. The function, the discrete function, the discrete functions do not have derivatives. Okay? Do not have derivatives. Derivatives cannot be defined for discrete functions. Okay? Yeah. So you have to use functions with continuous variables. The functions with continuous variable. So when you consider derivatives, you have to consider functions with continuous variable. Okay? Yeah. So here, let's consider the function with continuous variable x. X. Yeah. The limit of the same form, but we replace n by x. Yeah. But when we use x, x can take the continuous values. Yeah. So, for example, from 1 increasing to infinity, so all the values from 1 through infinity can be taken here. Yeah. Not discrete values as n, 1, 2, 3. Yeah. Any value between can be taken here. So that's the continuous version. And for the continuous version, then we can take derivative. It's legal to take derivatives for functions with continuous variables. Yeah. All right. So now we just apply the L'Hopital's rule, because here, if you look at the, check the indeterminate form, it's also infinity over infinity, right? So when x goes to infinity, log of x also goes to infinity. Yeah. Okay? Yeah. So then you can take the derivative of numerator function 1, derivative of denominator function, reciprocal. Yeah, so here the formula. 1 over that inside bracket constant natural log of a times x. The formula. Okay? All right. So then you want to simplify it. After simplification, when x goes to infinity, this limit goes to also, this limit equals infinity. Okay? Yeah. For the limit, we can write equal sign. Okay? Yeah. So actually, we do not have to write the arrow sign. We can write equal sign. Yeah. Limit equals infinity. Okay? All right. Yeah. But that's for the continuous variable case. Yeah. So we'll make the change. Yeah. So we need to go back from the continuous case to the original discrete case. Yeah. Yeah. So the computation we did is for the continuous variable. But at the end, we need to go back to the discrete case. All right. So our conclusion is the discrete case is also infinity. If the continuous case, the limit is infinity, then when we go back to the discrete case, its limit is also infinity. Yeah. So the question is how to see it. How to see it. Yeah. How to see it. Okay? Yeah. So here, let me explain. Yeah. Let me explain. Yeah. How to go from continuous variable case to discrete variable case. Yeah. All right. So that's based on the definition of the limit. When we consider limit, when x approaches infinity, do we specify any special way that x grows to infinity? We didn't specify, right? Yeah. So here, when x approaches to infinity, do you know how does x approaches infinity? how does x approaches infinity? No. Nobody specify it. Okay? Yeah. Nobody specify it. When x approaches infinity, the meaning here is you can take any specific way to make x approach to infinity. Any specific case. Okay? For example, you can take x equals 1.1 first, 2.3 second, 3.5, and so on, and or 1 square, 2 square, 3 square, okay? Yeah, goes to infinity. So many millions of different ways to go to infinity. Anyway, it is fine. Any of those millions of ways to go to infinity would work. Yeah, that's the definition of the limit. Okay, all right. Since any of those ways would work, can we take the discrete case 1, 2, 3, 4 to infinity? It also works. This specific discrete way would also work. That's one of the million ways, right? One of the million ways. Yeah. It also works. So when we take this specific way, we get this, our original limit. The discrete original limit. Okay? All right. So here, I spent so much time to explain this kind of details. Yeah, so the reason is try to convey the rigorous math proof here. Yeah. If we want to do the rigorous math proof here, so you need to consider all the details here. Okay? Yeah. Yeah. All right. The L'Hopital's rule, so you have to apply it on the discrete, continuous variable version, not discrete, continuous variable version. Yeah. So then, if you read our textbook at this particular point, yeah, it is not rigorous. Okay, our textbook just apply derivative on the discrete functions, discrete versions of functions directly. So that's not rigorous. Okay. So you need to be aware of it. Yeah, yeah. All right, so let's make a conclusion. So after our calculation, the conclusion is the algorithm with growth function n log m is faster, although this function, this growth function, increases slower than the second growth function, but the algorithm is faster. Well, because that means we need to use fewer number of comparisons. If we use fewer number of comparisons, so the algorithm is faster. Yeah. All right. So that after the amount of work we put here, now you get a conclusion. In the element uniqueness problem, the second method is faster than the first method. So that means if you sort the given array first, actually you can do faster than without sorting. Faster than you do direct comparisons without sorting. That's the final conclusion. Yeah. All right, for that element uniqueness problem. Okay. All right, so now at this point, so you know the concept of growth function, and you also know how to apply mathematical technique to calculate the, to compare the growth functions. Yeah. All right. Yeah. Part C, asymptotic notations. The abstract concept for this module, the most important concept in this module, asymptotic notations. C.1, Introduction to Asymptotic Notations. Yeah. All right. Yeah. So let's look at this limits of two growth functions again. Yeah. So when we consider the limit of the ratio of two growth functions, then we want to look at all the possible cases. Yeah. So we have these cases. Yeah. Yeah. Actually, the cases, yeah, in the previous slide, I already list the 4 cases. Remember? Yeah, so here, these 4 cases. Yeah. 0, non-constant, yeah, so here, this constant C should be non-zero constant. Now, infinity and other cases, the limit does not exist. Yeah. So the limit does not exist. Case. Okay? Yeah. All right. Yeah. The first case. Yeah. So let's look at these 4 cases one by one. The first case. Yeah. The first case, because the ratio goes to 0, so that means the numerator function increases slower, actually much slower than the denominator function, right? So when n goes to infinity, the numerator function increases much slower than the denominator function. That's the first case. So here we give a terminology, so we call this case the order of growth of f of m is less than the order of growth of g of n. Yeah. Here we use a concept, concept called order of growth. Yeah. So you may wonder, what's the meaning, exact meaning of this order of growth? Yeah. So I will explain it later. So here we use this concept, order of growth concept. Yeah. Okay? For comparison. Yeah. So we compare the order of growth of 2 growth functions. Yeah. So each growth function should have certain order of growth measure, number. Yeah. Yeah. But what's that number? Yeah. So I will explain later. Yeah. Soon. Yeah. All right. In this slide. Yeah. All right. The second case, the ratio constant C, in that case, the constant C, so here you can see these 2 functions pretty much increase with the same pace, right? Yeah, these 2 functions increase with the same pace. Yeah. If the first function doubled, the second function also doubled. If the first function tripled, the second function also tripled, and so on, right? With the same pace. Yeah. Because the ratio is the same non-zero constant. Yeah. So for the second case, we can say these 2 functions have the same order of growth. Okay? Yeah. Equality. Yeah. If we compare their order of growth, yeah, we get equality here. Yeah. The third case, yeah, just opposite of the first case. Yeah. Because f function increases much faster than g function. Yeah. So we say the order of growth of f of n is greater than the order of growth of g of n. Yeah. The case number 3. Yeah. But for case number 4, case number 4, we cannot do the comparison. We don't know. So if we want to see the difference between the order of growth, we do not know it. Okay? Yeah. Because the limit does not exist. We cannot say anything about the order of growth for case number 4. Okay? Yeah. All right. Yeah. So here, before we go to the next step, so let me explain this order of growth concept a little bit. Yeah. Otherwise, you may not feel very comfortable. Okay? For this abstract concept, order of growth. So what's that? You cannot feel about it, right? It's hard to feel about it. Yeah. How to imagine what's that order of growth? Yeah. Here, I want to give you some concrete understanding of this order of growth concept. Yeah. All right. So let's consider some simple case first. Yeah. When we look at the order of growth, order. Yeah. So first, the order concept. Order of a function. Do you know the order of function, that concept? Order. Yeah. So in a polynomial, do we have the order concept in a polynomial? Order and a degree. Yeah, actually order and a degree. Yeah. In polynomial, we have degree concept, right? Yeah. In polynomial, we have degree concept. Yeah. All right. And order is different from degree. Okay. Order is different from in polynomial. So here, in polynomials, in the polynomial context, we have degree and order concept. Okay. All right. So here the polynomial, if we just use our standard polynomial, this standard general polynomial, yeah, degree equals n. Okay, yeah. Order is one more than a degree, n plus 1. Okay, yeah. So that's the concept in the polynomial context. Okay, all right, yeah. But here the order it's different from that order. Okay, so here the order here is some abstract order here. Okay, abstract order here. Yeah, and here the order of growth. So we're talking about the growth functions. So we're talking about the growth functions. Or in the growth function context. Okay, in the growth function context. Yeah. All right. Yeah. So here, yeah. So here I show you a few examples, simple examples. Yeah. If the growth function equals n squared, yeah. So then, because when you look at that number, exponent number, then we make this order of growth two. Yeah. So that's the direct order of growth. Okay. Yeah. So n to k, yeah, general k. So then the order of growth just k. Okay. Growth. Yeah, growth. So here. Okay. All right. Yeah. Simple. Yeah. The simplest case. Yeah. But But so this is the simplest case. Okay. Yeah. Yeah. But sometimes, for some cases, for some relatively hard cases, the order of growth, it's hard to use specific numbers to represent order of growth. Yeah, so there are a few cases. It's hard to represent order of growth explicitly. Okay? Yeah, for example, so here let me give you a relatively hard case, an example. Okay? Yeah. For example, log of n. What is the order of growth? It's hard to use the previous simple way to represent order of growth. Okay? Yeah. Hard to write it out. Write it out. Okay? For log of n. Hard to write it out explicitly. Okay? Yeah. So there are some hard cases. So we cannot write specific numbers out as the order of growth. Yeah. So for that reason, when we talk about this concept, order of growth, yeah, many times we do not write explicit numbers out. Many times. Only for the simple cases here, we can write explicit numbers out. Yeah. For other cases, it's hard to write explicit numbers out. Yeah. We just use some abstract order of growth concept. Yeah. Yeah. So that's the understanding here. Okay? That's understanding about these first three cases. Well, three cases. Okay? All right. So next, we want to use compact notation. So here, let me erase this line to let you see what we want to do next. We need some compact notation for the first three cases. Yeah. Because for the first three cases, we use inequality or equality to represent the relationship between the order of growth of f function and a g function. You need to write many words. Yeah. So the expression is not that simple. So we want to use very simple representation for the first three cases. So here we need to introduce new notations for the first three cases. So what's that? All right. So case one, here we use this notation. F of n belongs to little o. Look at this little o thing. Little o of g of n. Yeah. So this little o, we call it an asymptotic notation. One of the asymptotic notation, little o. Yeah. Yeah. Its meaning is just this. Yeah. That is the meaning. Okay? The meaning, the limit ratio equals 0. The meaning. Okay? But here we use this special asymptotic notation. All right? Case 2, this time we use another asymptotic notation, big theta asymptotic notation. Okay? The case number 3, we use third asymptotic notation, little omega asymptotic notation. Okay? Yeah. So in this way, the expressions are much simpler. Yeah. So when we want to have discussions, yeah, so we do not need to write so many words. We can use this kind of compact notations, yeah, asymptotic notations. Okay, all right. So later I will give you the rigorous definition of some of the asymptotic notation. Yeah, so there are several. Yeah, there are several asymptotic notations, but I only give you definition for three of them. Yeah, three asymptotic notations. Yeah, all right. And the next, so here, next we need to consider case number 4, right? Yeah, because case number 4, there is no expression between their growth function, order of growth functions, and no asymptotic notation for case 4. Yeah. But we want to compare which function grows faster, which grows slower for case number 4. Yeah. But we cannot do the limit way. The limit does not exist. So we want to find a different way to study case number 4. Yeah. So next we need to consider a different way to study case number 4. Yeah. All right. So the way is using upper bound and the lower bounds between representations between those two functions, f function and a g function. Yeah. Objective. Yeah. So here, even if the limit does not exist, yeah, because this method we do not use limit. This method we will use inequalities. We will use inequalities. Yeah. Inequalities instead of limits. To avoid the technical difficulty of limits. Yeah. All right. So does not exist, we can still compare growth functions. Yeah. How to do it? Yeah. The function, g function, is usually a simple function, the growth function. Remember, after 2 rounds simplification. So the g function usually simpler, like n squared, n log n. Yeah. F function could be a complex function. Yeah. Okay? Yeah. All right. So then, use some constant multiples of g to approximate f function. Yeah. So here, we want to estimate f function. Yeah. But how do we estimate f function? We use constant multiple of g to try to bound f function, upper bound and the lower bound. Okay, 2 different bounds, upper bound and the lower bound. Okay, yeah, all right. Specifically, can we find 2 positive constants c1, c2 such that f function is between 2 constant multiples of g, the lower bound c2 g of n and the upper bound c1 g of n. Yeah. So that's the method we will use to compare the order of growth of these 2 functions. No limits here. In this method, no limits used. Only inequalities used here. Okay? Yeah. So this method works no matter the limit of the ratio of these 2 functions exists or not. Okay? Yeah. So the advantage of this method. The advantage. Yeah. So here you can see we have 2 methods when we compare the order of growth of two functions. So basically we have two different methods. The first method, the limit method. The second method, inequality. Upper bounds, lower bounds method. Yeah. These two. Okay? Yeah. All right. Yeah. So next topic, C.2. Define asymptotic notations. Yeah. So we still a few minutes. Yeah. We can only get started. Yeah. Big O notation. Yeah. Big O notation. Yeah. So in this part, C.2, I want to explain three asymptotic notations. The first one is big O notation, and two more. Second, big theta notation. Yeah. Third, big omega notation. Yeah. These three. Yeah. The most commonly used, the first one, big O notation. Yeah. The second most, big theta notation. The second most, big theta notation. Yeah. Yeah. Then the third rarely used. Yeah. The first two commonly used asymptotic notation in this class. Yeah. All right. Yeah. So the first one, let me show the definition of the first one, and then I explain this definition next time. Okay. All right. So first, the definition. Yeah. The complete definition here. For a given function g of n, the notation big O of g of n represents the set of functions. Set. Yes, this concept, I think you know it. Okay. Set of functions f of n that satisfy the following inequality condition. The condition is an inequality. All right, for this big O, inequality is there exists some positive constant c and some non-negative integer n naught, okay, n0, n naught, okay, such that this inequality holds f of n less than or equal to c times g of n for, yeah, so there is a condition, for all n greater or equal to n naught. Yeah. That's the full definition of this big O notation. Okay? Big O notation. Yeah. All right. Yeah. So although if you just read sentences in this formal definition, it may not be very hard to understand, but actually it's not easy to understand this concept well. Okay? It's not easy to understand this concept well. Yeah. So next time, yeah, because today we run out of time already. Yeah. So next time, at the beginning of the class, I need to spend some time to help you understand this definition well. Yeah. So there are some hidden meanings. I need to point out those hidden meanings in this definition to get better understanding. Yeah. All right, so let's complete this module 2, the remaining understanding these concepts. After that, I need to give you a few examples, comparing growth functions, a few basic examples. Yeah. So then we will finish module 2 next time. Yeah. All right, so that's it.